Hello everyone, I'm Guanhua Wang. Today I'm going to talk about my recent research project called Wavelet. We can achieve efficient DNN training with our novel Tick-Tock scheduling policy. It's a joint work with Wang, Jiang, Xiangjun Li, and Yang Stoican. Right now, the deep neural networks empower state-of-the-art results across many different applications, such as image classification, speech recognition, robotics control, and also game playing. However, the DNN training are often time-consuming. To speed up DNN training, there are two widely adopted approaches called data parallelism and model parallelism. In data parallelism, each machine holds a full copy of the model parameters and train locally on different input data partitions. After each training iteration, they need to do model synchronization among all the GPU or machines in use in this training job. In model parallelism, each machine only holds a part of the full model parameters, and they train simultaneously on the same input data. However, in either data parallelism or model parallelism, all the in parallel training tasks are Gang scheduled. Gang scheduling is the all-or-nothing scheduling policy, which means it either launches all the in parallel training tasks at once or launch nothing and wait for the resources to be available for launching all the in parallel tasks simultaneously. And we monitor the resource utilization of Gang scheduled training tasks. Here is a simple example of data parallel training using two V100 GPU. Here we train the Resident 56 on ImageNet 1K dataset. On the upper figure, it shows the normalized memory usage on each GPU, and at the bottom, it shows the corresponding computation usage. Now let's just look at one training iteration, which consists of one forward propagation and one backward propagation. On the upper figure denoted as the yellow line here, start from time 0.6 second. As the forward propagation starts, the corresponding memory usage starts increasing, and at the time of 0.8 second, it reaches the on-device memory upper bound. When we look at the bottom figure during the same period of time from 0.6 and 0.8, the corresponding computational usage is only less than 40%, which means this computation is memory bounded and leaves around 60% computation resources underutilized, which is denoted as the red shadow box at the bottom figure. During the backward propagation, as the yellow line shown on the upper figure, the memory usage starts decreasing, and there is a memory valley period shown as the red shadow box here from time 0.9 to 1.2 seconds. And during this memory valley period, the GPU memory is also underutilized. The reason why we have this consistent memory valley period during the distributed DNN training is because the Gang scheduling policy guarantees that all the training tasks reach their memory peak and valley period at the same time. Thus, one training task cannot leverage another training task's memory valley period. Thus, all the memory valley period are wasted during the backward propagation in the distributed DNN training job. We also conduct system monitoring of the resource utilization in model parallel training. Here we use full V100 GPUs, and we train BERT by adopting or without adopting the pipeline parallelism. As you can see on the red figure denoted as the red shadow box, the memory valley periods consistently exist in either adopting pipeline parallelism or without adopting pipeline parallelism. Similarly, because the computation is memory bounded, the computation resources is consistently underutilized in both data parallel training and model parallel training, denoted as the red shadow box across the bottom figures. However, by adopting the state-of-the-art job multiplexing schemes such as Guanhua or Salus, it can increase the GPU memory and computation utilization. But this kind of approach doesn't contribute to the training process of a single job. And this is the reason why we propose Wavelet, which is trying to improve system efficiency in single job case. Here on the left, two figures show the memory usage and computation usage of the vanilla data parallel training tasks. And we call this original data parallel training task as the take-wave training tasks. Because the memory value pair consistently exists during each iteration of the original take-wave training tasks, we inject another wave of training tasks, what we call the talk-wave tasks, by intentionally adding some long-chain latency so that the talk-wave training task forward propagation can happen during the take-wave or the original wave training task's backward propagation on the same GPU. Thus, by interleaving the peak memory usage between take-wave training tasks and talk-wave training tasks, it can achieve near optimal on-device memory usage, as you can see on the right upper figure. Consequently, it also increases the computation usage from less than 40% to around 60%, as shown at the bottom figure on the right. So the abstraction of data parallel training using Tick-Tock scheduling is as follows. On the left figure, the capital F or B means forward and backward propagation, and this blank box means the take-wave training tasks. On the right-hand figure, which is our Tick-Tock scheduling, we intentionally add some latency so that the injected talk-wave training tasks forward propagation can happen during the original take-wave training task's backward propagation. Similarly, compared with the gun-scheduled single sequence of computation kernels on a GPU, in our Tick-Tock scheduling, here we can launch two sequences of computation kernels simultaneously on two different CUDA streams. Thus, it increases the computation utilization compared with the gun-scheduled training tasks. This figure shows the vanilla model parallel training iteration, which consists of a forward propagation and a backward propagation in this full GPU setting. Here, in each time slot, there is only one GPU working. And here, F and B with superscript and subscript of X, Y, Z means forward or backward at GPU X with the model partition Y on batch Z. As shown in the previous resource utilization figure, in model parallel training, the memory valid period actually is much longer compared with the memory valid period of the data parallel training session. So instead of inject just one talk wave tasks, here we inject three talk wave tasks, denoted as the blue, green, and orange boxes here on different batches. And different from the pipeline parallelism where each GPU always holds the same model partition during the whole training session, here on each GPU actually we swap the model partition in a round-robin fashion. For example, here on the GPU 0, denoted as the red figure here, on the first time slot it works on model partition 0, and on the second time slot it works on the model partition 1, and then 2, and then 3, so on and so forth. Here we briefly illustrate our evaluations on both data parallel and model parallel trainings using our Wavelet Tick-Tock scheduling. In a single machine case, which consists of 8 V100 GPU, we tested on VGG and ResNet training on ImageNet 1K dataset using 2 GPU, 4 GPU, and 8 GPU. And this figure shows a normalized throughput speedup compared with the original data parallel baseline. And as you can see in this figure, we can achieve up to 1.88x speedup over the data parallel baseline here. For the data parallel training in cross-machine setting, we conducted on two different machines. Each one has 8 V100 GPUs. And here the notation of 8 plus 8 means we use 8 GPU on both machines, and 4 plus 4 means we use 4 GPU on both machines. So in this case, we can achieve up to 1.18 speed up over the data parallel baseline. Another thing worth mentioning is that in this cross-machine case, actually we perform slightly worse in several cases compared with the data parallel training baseline. It is because the cross-machine load bandwidth network is the bottleneck. And in our Wavelet Tick-Tock scheduling, because we inject one additional talk wave tasks, it also introduces extra communication overhead of model synchronization of the talk wave tasks, thus make it worse compared with the data parallel training baseline. For the model parallel training in both single machine case and cross machine case, we tested VGG19 with batch normal and also the BERT training. And in these two cases, we can actually achieve up to 6x speed up compared with the corresponding model parallel baseline with or without adopting pipeline paradigm. So the summary is there is a wide range of distributed DNN training jobs that are memory bounded on the accelerators. And for a single job training, the gun scheduling policy leaves memory valley period underutilized. Wavelet interleaves peak memory usage among different waves of training tasks via our Tick-Tock scheduling policy. And for a single job, Wavelet can achieve up to 1.88x speed up in data parallel training and up to 6.7x speed up in model parallel training using the same group of accelerators. If you have any questions, you can reach out to me with the email at the bottom.